So the best way to talk about this further is to just jump in and let's look at some actual spectra. So the spectrum we have here is the spectrum for hexane. It's a 6-carbon molecule. It's fully saturated, so it has the maximum number of hydrogens, which is 14. So C6H14. What is the overall mass then for hexane? Well, if we add this up, we get a total of 86. Now, do we see a peak for 86 in this spectrum? We see a peak at 86 right here. So we would call that peak our M plus or our parent peak because it represents the entire molecule. But you might notice something a little bit odd here. Do you notice that there's actually a peak 1 mass unit higher at 87? What's at 87? So how do we get to a higher mass than what exists for hexane? Because there's nowhere that we could just put another hydrogen on there. Well, another thing to keep in mind with mass spec is that with mass spec, we're actually seeing individual molecules of hexane here, or of whatever compound we're looking at. So if we look up isotope data for carbon, we can find the table down at the bottom for the 2 naturally occurring isotopes for carbon. C12 is about 99% of the natural abundance. And C13 is just over 1% of the natural abundance. So what if we had a molecule of hexane, C6H14, that was made up of 5 carbon-12 and 1 carbon-13? In addition, of course, to the 14 hydrogens. Well, now, instead of adding up to 86, we would find that the mass now added to 87. But there's also a second thing to notice. The ratio between that M plus and now what we're going to call, because it's 1 higher than the parent peak, the M plus 1 peak, is roughly based on the number of carbons that exist within a molecule. Not always, and we don't spend a lot of time on this because there are many cases where this doesn't actually work or work as well as we'd like it to. But sometimes you can find a ratio between the M plus and the M plus 1 peak that helps you to determine the number of carbons in the molecule. All right, what about fragments? Are there fragments that we can identify? Well, what happens if we start breaking this molecule apart? So let's say we chop off a methyl group there. So we had C6H14. If we chop off a methyl group, we end up with C5H11. The mass for C5H11 is 71. And here we see a small peak, but still a peak present at 71, which is our M minus 15 peak. We could, instead of just chopping off 1 carbon, we could have chopped off 2 carbons. That would have given us C4H9 plus, or a mass of 57. And we can see that it is this large peak. And we can continue through the compound. We could cut off 3 carbons. That would get us to C3H7 plus, which has a mass of 43. And finally, we could cut off 4 carbons and go to C2H5 for a mass of 29. A couple other things to note. In this case, our largest peak is set at 100. Is that always going to be the case? Well, notice that the scale on the y-axis is not intensity, but relative intensity. So the way this typically works is that the largest peak gets set to 100, and then every peak is relative to that. So we were able to identify about a half dozen peaks in this spectrum. But there's a lot more. What are all of these other peaks? Well, that's one of the things about mass spec sometimes. Sometimes we can't identify every peak. As we've already said, there's all sorts of weird things going on under mass spec conditions, and most of these spectra may have some fragments that we can't fully identify. And that's not a problem, it's just something that we have to accept sometimes. Now, why are the peaks different sizes? Well, the sizes of the peaks are based on abundances. In other words, how prevalent that ion is in our sample. And that prevalence is then based on stability. So some carbocations are more stable than others. And if the carbocation is more stable, we're likely to have more of it. So what are carbocations stabilized by? The most common thing? Is the more substitution we have, the more stable they are. So a tertiary cation, like this one, and by tertiary cation we mean that the carbon of the carbocation is bonded to 3 other carbons. That's more stable than a secondary cation, is more stable than a primary cation, is more stable than a methyl cation. So why is it that more substituted carbocations are more stable? So this has to do with something known as hyperconjugation. So first of all, we want to say that a carbocation is generally going to be sp2. So carbocations are sp2 hybridized with an empty p orbital. And so if we have a CH bond that's adjacent to our carbocation, such as we have here, here's our empty p orbital, a CH bond on a neighboring carbon, such as this one, is able to align with the empty p orbital. And as a result, it donates electron density into that empty p orbital. So hyperconjugation is this effect that the overlap of orbitals allows a filled orbital to share electron density with an empty orbital. And so, as should make sense logically, the more of these carbons you have that are adjacent to your carbocation, the more bonds you have that can donate electron density, and the better it helps to stabilize the carbocation. In addition to this effect, the other major item that can help to stabilize carbocations, probably not surprisingly, is resonance. So if you had a cation next to an aromatic ring, compared to one that's just next to one that's not aromatic, our molecule here on the left is going to be able to, through resonance, share that positive charge. And we've talked about a number of times in this course that the ability to share a charge always makes it more stable. And an illustration we can see of just how well that works is with the next spectrum that I'm going to show you. So this is the spectrum for ethylbenzene. Chemical formula C8H10. Total molecular weight is 106. And so you can see we have a peak here that's the M plus peak here at 106 that represents our entire molecule, just missing an electron. As we saw with the previous spectrum, we also have a peak that's one mass unit higher at 107, representing a C13 in the molecule. But what is our largest peak in the spectrum? Well, it's this big peak here at 91. How do we get from 106 to 91? Well, we lose 15. Now, one thing you should start to notice as you start looking at more and more of these spectra is that you should start to see patterns, and that you should start to see that we have the same differences, same amount of mass that we lose over and over and over again. And this 15 is a number we've seen before, right? 15 is a methyl. Well, where can we lose a methyl? Well, in this molecule, there's only one methyl group that we can lose. And so if we lose that methyl group, we get this carbocation that you can see is very much, or is actually the same one we talked about on the previous slide. It's a primary carbocation, so that would suggest to us that it's not very stable. But because of the resonance, it makes it a very stable cation. And you can see very easily that given that the relative intensity of this peak is 100, the next largest peak in the spectrum was the parent peak, which had a relative intensity of around 40. And so that indicates to us just how stable this carbocation is compared to any other carbocations that can form. The next one you might expect to see is if you fragmented off the entire ethyl group, which would just give you an aromatic ring with a positive charge. C6H5 plus has a mass of 77, and we do see that peak. It's fairly small, but it's here. But beyond that, we don't see a whole lot. There's some small peaks in the rest of the spectrum, but nothing that looks terribly significant. And that's because aromatic rings, as we're going to learn over and over and over again, are very, very stable. And so even under mass spec conditions, it's really tough for them to break apart. And so as you can see here, even under these conditions, we don't get the aromatic ring to break apart at all.